Welcome. So we're going to begin this lesson on derivatives of trig functions with a little review. All right, so here we have all of our derivatives, and we've gone over these. All right, derivative of sine x is cosine x. Derivative of cosine x is negative sine x. Derivative of tangent x is secant squared x. Derivative of cosecant, actually I'm going to go over derivative of cotangent, because it kind of goes together. Derivative of cotangent is negative cosecant squared x. And then derivative of cosecant x is negative cosecant x cotangent x. Derivative of secant x is secant x tangent x. And by the way, it really doesn't matter if you were to reverse cotangent and cosecant and tangent and secant because you're just multiplying them. We just have a tendency to write the cosecant or the secant first. Helps you remember it, I guess. All right, so let's do a few simpler trig derivatives, and we'll also review tangent lines and normal lines, and then we'll take a look at trig functions and combine that with some of our product rules and chain rules and quotient rule. And though we've done some of that, we're going to add in some more functions. We'll do a little bit more advanced work. All right, so we want the slope of the tangent line of f of x equals tangent x. First thing we have to do is take the derivative. All right, come on, there we go. All right, so we're taking, actually maybe I should write the function first. It surprised me because it actually started to write it first. It almost never does that, and now it's not writing. That's what it usually does when I begin a new podcast. There we go. F of x equals tangent x, and then the derivative f prime of x would be secant squared x. All right, so now we just need to evaluate to find the slope of the tangent line. Evaluate at 2 pi thirds. All right, so that's going to be, and a way you can think of this is it's secant 2 pi thirds and then the whole thing squared. All right, so let's plug in. Oops, let's evaluate using a reference triangle. That is not a very good looking coordinate plane. There we go, it's a little bit better. All right, so 2/3. All right, well this would be pi halves. So it's more than pi halves. It's right over here somewhere, right, because this would be pi. All right, so it's less than pi, but more than pi halves. All right, and if this distance is pi, same as 3 pi thirds, right? The distance from here to here is 2 pi thirds, and right here we have pi thirds. Right? Not very clearly written, but that says pi thirds. Right? And I knew I couldn't move it. But here, I'll write this nicer pi thirds in here, and then I'll just recopy what I wrote. Right? So add that, what I just wrote. There was 2 pi thirds. All right. All right, so pi thirds is the same as 60 degrees, right? Because 180 divided by 3 is 60. And so a third of pi is 180, right? And so a third of that would be 60. Opposite 60 degrees is the square root of 3. The adjacent side is 1, and then the hypotenuse is 2. We're looking for secant. As a little reminder, secant is the reciprocal of cosine, right? So cosine is adjacent over hypotenuse. Secant is hypotenuse over adjacent. All right, so that's going to be 2 divided by 1, which is 2, right? So secant, in this case, secant 2 pi thirds is just 2 over 1, or just 2. I'll write it in there. All right, so this is going to be, so f prime of 2 pi thirds is just going to be 2 squared. How easy is that? So f prime of 2 pi thirds is 4. There we go. All right, so you evaluate the secant first and then square it. All right, that's all there is to that one. Let's try another one. All right, so we want to find the slope of the normal line, right? And it looks like I already evaluated. Well, I have some things up there. I'm going to erase this. That was more than I wanted to include initially. All right, so first of all, we need to take the derivative of cosecant. All right, so the derivative of cosecant is cosecant x. There you go. Cotangent x. Right? So if you forget, kind of a way you can sort of maybe remember it. Let's go back to that list. All right, so derivative of tangent is secant squared. So derivative of secant ends up being secant tangent. I mean, it has nothing necessarily to do with that. It sort of does. But that's a way you can remember it. All right. Remember, we went through all those derivations. But just the kind of way you can remember it. So tangent is secant squared x, then secant is secant tangent. Right? And cotangent is negative cosecant squared, and cosecant is negative cosecant cotangent. Right? Just a little memory device there. We actually derived them, right? And we can go back to the derivatives later on if you want to take a look at those. But for right now, let's just apply what we've learned. All right, so we have our derivative there, and we need to evaluate. All right, so we have f prime of 5 pi fourths, all right, is equal to cosecant 5 pi fourths times cotangent 5 pi fourths. All right, and now we'll evaluate that. All right, let's draw a little. I think I had kind of the answers there, but I want to evaluate, go through that with you. All right, so of course this is pi, so we are right there. We're 1/4 more, right? Literally would split that in half if I could draw it well. All right, so this angle here is 5. I wanted to make a pi, not a 4. 5 pi fourths. Right? So this much is just pi fourths. That's a 45, 45, 90 triangle. This is 1, this is 1, this is the square root of 2, except since it's in the third quadrant, these two are negative. All right? So now we have our reference triangle, cosecant. Right? That's the inverse of sine. So it's going to be the hypotenuse over the opposite. Although here, whether we're using the opposite or the adjacent, it's going to be the exact same thing. And then cotangent is adjacent over opposite. The reciprocal of tangent. There we go. All right, so cosecant, hypotenuse here is square root of 2. And the opposite side is -1. That's going to make that negative square root of 2. And for cotangent, adjacent, they're both -1, right? Adjacent and opposite, both -1. So that's just going to be 1. All right, so now let's finish evaluating here, because we're going to replace cosecant 5 pi fourths with negative square root of 2, and we're going to replace cotangent 5 pi fourths with a big old whopping 1. All right, so f prime of 5 pi fourths is just going to be negative square root of 2 times 1, so that's just negative square root of 2. All right, so that's the slope of the tangent line. All right, so we're going to take the reciprocal of the slope of the tangent line to get the slope of the normal line. This one actually didn't ask us to find the equation in point slope, so I think we save that, and let's just find the slope that we need. All right, so to take the reciprocal of the slope of the tangent line, if we've got negative square root of 2, the reciprocal of that is just 1 over that. All right, so the slope of the normal line, just put normal line slope, is going to be, and instead of negative, it's going to be positive. So 1 over the square root of 2 is fine. Or if you wanted to rationalize it, it would be the square root of 2 over 2. And that's the slope of the normal line. So we've done 2 little review problems, and that took us 10 minutes. Now let's go through the meat of this lesson, and that is combining trig functions with some other rules. All right, so chain rule comes up an awful lot, because if you're taking sine, cosine, tangent, cotangent, cosecant, secant of anything other than a single variable, an x, a theta, you have a chain rule. So it comes up an awful lot. So as a reminder, it's going to be the derivative of the outside function times the derivative of the inside function. So this is composite functions. And most of the time, our trig functions are composite functions. All right, so if the outside, f of u, is a differentiable function of u, and u, g of x, is a differentiable function of u, then y equals f of g of x is going to be differentiable. If the outside is and the inside is, and quite honestly, right now, I'm not going to give you anything that's not differentiable. I'm not going to try and trick you. All right, we're going to take the outside. All right, so that would be f prime of g of x, derivative of the outside function, and then the inside, the g prime of x, that would be the derivative of the inside function. All right, so let's take a look at some chain rules here. So anytime you are taking a derivative of a trig function and the parentheses inside part, and we have an extra piece here, I think from when I previously done this problem, is not an x, a t, a theta, a whatever, one single variable, you're going to have to use the chain rule and take the derivative of the function in the parentheses. And a little helpful reminder there, put your coefficients of x to a power in front, right? You don't want to make that look like you're taking the cosine, sine, or whatever of that. All right, so outside function is cosine blup. Right, so the f of x part is cosine blup. And the inside part is the 4x to the 5th. Right, so the derivative of cosine blup is just negative sine blop. Okay. And in this case, the blop equals 4x to the 5th. Derivative of 4x to the 5th is just 20x to the 4th. That's just a power rule. All right, so our derivative, I'm going to move this down just a little bit. We're just going to multiply those two things. Right? We're going to have f prime of x and times g prime of x. Right? So f prime of g of x. Actually, no, let's just write it as, or we're just going to write it as dy dx there. And then I have to think about, do I got the primes in the right spot? So dy dx is going to be equal to, let's put the 20, they can wait all day for you to come up. Come on, there we go. You got to coax these boards along. Times sine, and actually I don't need a parentheses in there. I don't even know why I put a parentheses in there. It's just extra stuff. Now, when you need a parentheses, make sure you put it in. If you really don't need a parentheses, I mean, it's not wrong, but pen down, there it goes. And sine 4x to the 5th. All right. I have no explanation for that. I think it was thinking about erasing from before. All right, come on. Sine 4x to the 5th. There we go. My goodness, it didn't take so long to write. All right, so we've just multiplied the derivative of the outside times the derivative of the inside. And just put those coefficients in front. Make sure negatives go in front. All right, negatives coefficient. Let's do another problem. All right, so here we take the derivative, we want the derivative of cosine 4x squared minus 7x plus 5. All right, the outer function is the cosine. All right, so we have cosine blup Let's just call it u. Cosine blop. The inner function is the, and we'll call that v, is the 4x squared minus 7x plus 5. Derivative of the outside, right, it's going to be negative sine blop. And the blop, let's just fill in the blop. 4x squared minus 7x plus 5. Derivative of the 4x squared minus 7x plus 5, that's just the power rule, 8x minus 7. All right, so here you're going to need to use parentheses to show that you're multiplying by 8x minus 7 and not just the last number in that. All right, so our derivative, dy dx, is equal to 8x minus 7, and put that first. It looks awkward to be second. And now I don't need to use parentheses for the cosine part. Oh, excuse me, not the cosine, the sine part. But then I'll use the parentheses for what we're taking the sine of. And don't forget we had a negative here, right? So let's add that negative. So negative for 8x minus 7 in parentheses. And then we can just put the sine. And now we'll need parentheses because we're taking the sine of the whole thing. 4x squared minus 7x plus 5, and that's all there is to it. All right? Sometimes these can get a little long just because you have to write a whole bunch. Right? But this one wasn't very complicated, I don't think. I hope you didn't think so too. All right, so here we have a product and a chain rule. The product part is that you have sine t times secant squared t. The chain part is that, well, you have secant squared t and not just secant t. All right, so for a product rule, it's the first times the derivative of the second plus the second times the derivative of the first. All right, so the first is sine t, and the derivative of that is cosine t. That wasn't too hard. You can think of secant squared t as secant t all squared, right? And then you'll remember that you're going to use the power rule here. Right? So you're going to take the derivative of blop squared. Right? And that's just 2 blop. And of course, inside our blop is secant t. Now we need to take the derivative of the secant t part, right? The inside, right? So this was the outside. Now we need the inside, right? Let's just call that let's call it w. W equals, right? And that was the secant t. The derivative of secant t is going to be secant t tangent t. And that's a lot of t's. All right, so our derivative, h prime of t, is going to be the first sine t times the derivative of the second. And then the derivative of the second is we need the outside. I'm going to box it. We need this part. And if I had some more space, I probably should have written it. And then we need this part. Like written the derivative all by itself, all finished off. But that's okay. We'll just put it in now. All right, so we need the outside, which is 2 secant t. And we're just multiplying these things. I'm just going to put parentheses around to show we're multiplying. I'm taking the secant of 2 secant t. And then we have plus, I'll just write below, the second, which is the secant squared t, times the derivative of the first, which is cosine t. All right, so now any coefficients need to go in front. There's just one, there's the 2. All right, and then the order you write them in really doesn't make a difference. H prime of t, you could put secant first, you could put sine first, you're just multiplying them. We'll put the 2 first, and I'll just leave them in the exact same order they're in. Sine t, and I can drop the parentheses at this point. Secant t, and then we have plus secant squared t cosine t. And there we go. There's our final derivative. So I don't I mean, not too complicated. And if you label things, you're less likely to make a mistake, all right? That labeling over there, then I can make sure we have all the parts. And you can even have written the derivative. I didn't really finish the derivative for secant squared t. I had the outside and the inside, and it kind of ran out of space, and we just put it up here. I mean, I did in the end finish it, but I didn't finish it by itself. All right, so here we have cosine cubed 3x squared. You can think of this as sine 3x squared all cubed. Right? It's just a convention. We put the exponent right next to the sine, but it's the whole thing that's cubed, not just the sine. I know when I was a student, I found that confusing at first until someone said, "Hey, it's this." Right? It's this. And then I'm like, "Oh, okay, that's fine. I got it." All right, and hopefully you'll get it too. All right, so now we have 3 chains here. This is a repeated chain, actually. All right, and actually I'm going to go over repeated chains, but I happen to have a repeated chain before I go over repeated chains. That's okay. We have, so let's just label everything. U is the outermost, because we go outer to inner. So U is the blop cubed, right? Then V, got to move in now, that's the sine blop. And then W, that's the blop. W is the blop. The blop is W, 3x squared. All right, so the first blop, this blop here, that blop is, and I'll actually write it, what's in there, is sine 3x squared. So when we finish taking the derivative, we'll fill in the blop. That's the sine 3x squared part. The second blop is the 3x squared part. That's the bloppiest blop, because it's in the middle. It's in the total inside. You're going to learn all new words here. Blop, bloppiest. All right, so du is just going to be 3 blop squared. And then we'll just replace the blop with sine 3x squared. That doesn't change. That's why I just put a blop in there sometimes, because then I'm not worrying, I'm not thinking about it, right? I'm just thinking about what's the derivative of something cubed. It's 3 times that something squared. All right, then I got sine blop. Right? I'm not worrying about what the blop is. The derivative of sine blop is going to be cosine blop, right? And then we'll fill in the blop. And then finally, the derivative of 3x squared is 6x. All right, so now we'll put this all together. Where? I don't know. Here, because I already have these written down. And so even though it's very nice that I wrote them there, we'll get rid of that so I can write more. All right, so our derivative, right, dy dx, is going to be the outermost part, so 3, and the blop is sine 3x squared. Kind of missing a parentheses here. Got a parentheses that doesn't close. And then times the dv, right? So our derivative here, I'm going to write this. dy dx is just going to be the du times the dv times the dw, right? We just multiply all the derivatives together. The derivative of the outside, the inside, and in this case, the inside. All right, and so we've got, it's going to be the outside, then our little bit more inside is cosine 3x squared, and finally the last part is the 6x. Right? We just want to pretty this up, because this is not a good way to have our answers look. Right? You need to combine those combinable things, those coefficients, the things that aren't the trig function of something. Right? We can multiply 3 and 6x, and we should do that. Right? And so that's going to be 18x, and then we have the sine. Did I leave off a, oh, sorry. Somehow that just didn't get written. There we go. Let's start our square back. 18x sine squared, 3x squared, because we usually put it there, right? It's fine to put it there for now. on the outside. And then let's move back to the inside where it normally goes. 18x times sine squared 3x squared, and then times the cosine 3x squared. And there we go. There's our derivative, right? So just take your time. Don't get concerned about what's on the inside until you've taken the derivative of the outside, and then you can just focus on the next part, right? And blocks can help you out. Let's do some more. All right, so first, second, third derivatives. So I'm briefly going to go over higher derivatives in this lesson. And then I'm going to do the same thing with some trig functions. And the reason I can stick this in right now is it's not that difficult. And it's really easy if it's a polynomial, right? So the first derivative, that symbol there means first derivative. I'll put it at the end here. I'm just going to take the derivative, right? So the derivative of x to the fourth is 4x cubed, plus derivative of 2x cubed is 6x squared, and the derivative of the negative x is negative 1, the derivative of 5 is 0. If I put this with two prime symbols, this is the second derivative. I just do the same thing again. And on a polynomial, it's pretty easy. Now, if I have something more, if I have products in here, they start to get really messy. But for a polynomial, each time I take the derivative, it actually gets easier. All right, so now I've only got three terms instead of four terms. Derivative of 4x cubed is 12x squared. The derivative of 6x squared is going to give us 12x. I'm just using the power rule here. And the derivative of the negative 1, that's 0. If we see this, that's the third derivative. And if you thought the first and second were easy, the third is going to be 24x. The derivative of 12x is just 12. What if we want the fourth derivative? You can put it in like that. Sometimes people also just put a 4 in there. But we'll do the fourth derivative. All right? So now, fourth derivative, it's getting even easier. What's the derivative of 24x plus 12? Just 24, because the derivative of 12 is 0. What if I want the fifth derivative? Well, that's going to be 0. And the nice thing about polynomial functions, and this will come in handy in a much later lesson, is that when you keep taking the derivative, eventually, at some point, they're going to go to 0 because you're going to end up with a constant at the end, because at each time on a polynomial, the degree keeps going down. So pretty easy to take the derivative on polynomial functions. What about trig functions? All right, so here we had first, second, third, fourth, and fifth derivatives for a polynomial. What about trig functions? All right, so let's do higher derivatives. And this one is for trig functions. All right, so if we have f of x equals sine x, the first derivative is going to be cosine x. Well, what's the second derivative going to be? All right, well, derivative of cosine x, that's negative sine x. Well, what's the third derivative going to be? Derivative of negative sine x, right? Well, that's going to be negative cosine x. What's the fourth derivative going to be? Well, derivative of negative cosine would be a negative sine x. So that would just be sine x. And guess what? This whole process would repeat over and over and over again, because the fifth derivative, I'll be back to cosine x. So sine and cosine, they just cycle back and forth. And if I were to start with cosine, right, I'd get the same thing, only I'd get it one derivative sooner. Right? Because if cosine x is my function, then my first derivative is negative sine x, and my second derivative is negative cosine x, and my third derivative is sine x, and then the fourth derivative would be cosine x. Right? But they just cycle back and forth between them. How about some of the other trig functions? Right? What if we looked at tangent x? Right? So if we have f of x equals, and we're not going to go as far with the other trig functions. So f of x equals tangent x, f prime of secant squared x, and now that's not as easy as sine and cosine because now I have a chain rule. So the second derivative, right, so this is technically secant x all squared. So the second derivative would be 2 secant x, and then I have to take the derivative of secant x, which would be secant x tangent x. I could simplify that. I could multiply the two secants together. So f prime double prime of x equals, maybe I won't write the double prime again. That's going to equal 2 secant squared x tangent x. Well, that didn't get simpler. That got more complicated. And if I took the third derivative, now I've got a product rule. And now I would have the first 2 secant x times the derivative of tangent x. Right? And the derivative of tangent x here is secant squared x plus the second, which is tangent x, times the derivative of the first one. And well, we already know what the derivative of this part is, of secant squared x, right? Because we just did that. That was, we did that up here, right? So we had secant squared x, and we took the derivative of secant squared x, and we ended up with 2 secant squared x tangent x. So the derivative of secant squared x would give us 2 secant squared x tangent x. And now, if I clean this up, we'd end up with 2 secant 4x plus 2 secant squared x tangent squared x. So you can see that's just getting more and more complicated, and we're not going any farther than that. And you get the same kind of things whenever you figure out the higher derivatives on the other trig functions. So sine and cosine, they're nice and easy. They just bop back and forth between one another. But any of the other ones, right away you get chain rule, and you get product and chain, and it gets a little tricky. Right? But so the point of this isn't so much so that you know the first of all, the point was so that you know how to take a higher derivative, that you just keep taking the derivative again. But also that you can see that some trig derivatives are easy to take higher derivatives of, right? It's easy for sine and cosine. And then other functions, not so easy, right? So we're going to have to be really careful when we're solving these ones out, right? And hopefully, because I didn't give myself much space, so I had to kind of talk my way back and like say, hey, remember I just found the derivative of secant squared x, and that was 2 secant squared x tangent x. Right? And so that's why I just plopped it down there. And then we had it times a tangent. And so hopefully that sort of made sense to you. But the goal really wasn't so that you would necessarily be finding the derivative of tangent x, but just that the higher derivatives for tangent, but just so that you can kind of see the difference. And know how to take higher derivatives in the first place. And I have that covered for a reason because I'm skipping past that. All right, so let's take a look at this one. And I think that's going to be, you know what, this might be a good place to stop this video. I'm going to stop this video and come join me in the next video where we solve more problems like this. Oh, and we will go back to that problem we skipped on a video, right? On the last set of videos. Right? Bye for now.